for us to answer, to be able to answer that question. So we have, we can talk of, scalar quantity. Scalar quantities as well as vector quantities. So when we talk of scalar quantities, we are talking of quantities that have distance and speed. Okay, they involve distance and speed. So those are scalar quantities. Now, when you talk of distance only has the magnitude, like how far. Okay, there's no direction. Okay, you're welcome, Chirufia. So scalar quantities, we say on scalar quantities we have distance and speed. Okay, now distance is a scalar quantity because we are saying it only has magnitude, it doesn't have direction, it just has magnitude. So if you want, you can get your car and start going round about. You're just going round. There's no direction, but yet your car will show that you have moved for 5 kilometers. 5 kilometers. There's no direction, you are just moving around. Or if you like, you can go like this, like this, like this. So from this point, you come to that point. There's no direction. So there's no direction, it's just a magnitude. So maybe this can be 5 kilometers, but there's no direction. So that's what we're talking about. So distance is a scalar quantity. Then speed also doesn't have direction. It just has magnitude. So it can be whatever it is that we are looking at can be moving at a very high speed yet without direction. Who can give us an example of an object or anything that can move at a high speed or whatever speed yet without direction? Anything that you can think of. Quickly. Okay, maybe there's nothing, but when you light a fireworks, when you light it, sometimes you find it will be spinning, and then it explodes. Okay, it will be moving at a high speed as it is spinning, not until it explodes. Okay, so that can also be an example of how speed operates. So speed doesn't have direction, it's just speed. Whether you are moving in circles, you are moving at a certain speed, there's no direction. So that's why we are saying speed is actually a scalar quantity. A scalar quantity. Now let's talk of vector quantities. So let's talk of vector quantities. Let's talk of vector quantities. So with vector quantities, we are saying these, they have displacement and velocity. So displacement and velocity. Okay, so these, they have displacement and velocity. Now displacement has direction. Okay, displacement has direction, and also velocity has direction. Displacement has to do with distance as well as direction. So if we are starting from point A here, and then we move like this to point B here. This is what we call distance. So this is distance. but the displacement is this. So this is the displacement. This here, it's displacement and it has direction. So you need to mention the direction whenever you're dealing with the displacement. Yeah, but with distance, there's no direction. It's just whatever distance that you have, whatever x kilometers or meters or whatever it is. So that's to do with the distance, and the displacement has got direction. Then also velocity. Velocity also has got direction. So when you're talking about velocity, you actually say since velocity is the rate of change of displacement with time. Okay, so it's the rate of change of displacement with time, while speed is simply the rate of change of distance with time. Okay, that's why it is measured in meters per second. Okay, then displacement, velocity rather, we're saying is the rate of change of displacement with the time. So if since displacement has got direction, so even velocity also should be associated with the direction. That's why there is usually you hear to say, okay, the ship is moving at so much speed heading north, or the plane is moving at this speed, at this velocity heading southwards. So there's usually when you're dealing with velocity, there's usually direction that is given as well. So direction will always appear somewhere when you're dealing with velocity. So that tells us velocity is actually a vector quantity. It doesn't only have to do with the magnitude, but it also has the direction. While scalar quantities, they only have magnitude, they only deal with magnitude, there is no direction there. So if you had time to go through the notes from the book that I sent to you, so you'll be familiar with what we are talking about here, and nothing will be a challenge. So if in case you need further readings, you can just go to the notes that I sent in the group, and then you'll be able to get everything there. Okay, so when we talk of velocity, there's velocity, there are about 3 formulas that we use to measure velocity or to calculate velocity. So the first one we have is V is equal to U A T. Okay, where V is velocity, U is initial velocity, and A is acceleration, and finally T is time. Yeah, so this is the first formula we have for velocity. So the question itself that you are being given will guide you as to which formula you are going to use. So we'll see, we'll check, we'll try to do 1 or 2 questions, then we see what can happen and how to use these formulas. So the second one is V squared is equal to U squared plus 2AS. Okay, so as usual, V here is for velocity, then U is still for initial velocity. So perhaps everything else is okay, is the way it was there up. Maybe let me just introduce something new here, which is S. S being the distance. Okay, so that is the formula, the other formula that we can use. Then the other one again we can use is the other one we can use again is S is equal to UT plus half AT squared. Okay, so s is the distance, u is the initial velocity, t is time, a is acceleration, t is time again squared. So those are the formulas that we use when we are in this topic that we are looking at, when we are dealing with velocity, distance, and the like. So before we can move actually from this question to other questions, the next time we meet, we need to also look at the speed time graphs, because they are also related to what we are talking about here. So I'll give you questions also on the same. We need to go through on the same, the speed time graph, before we can move to the next question, which has got force and other stuff. Okay, so acceleration, when we talk of acceleration, under speed time graph, maybe to just touch a bit, or distance time graph. So if you have, just to touch a bit, we'll come back to this as a topic. So when we are looking at a distance time graph, if we have something like this, then we have this, we have that, and then we have this. So distance here in kilometers and time there in hours, depends on what the reading you are using. You can also reduce it to meters per second or kilometer per hour. So what it means is that if you move from 0 to x here, let's say to h, and here to x, and here to y. So let's say we have a, b at these 2 points. So between 0 and x, okay, as time is increasing, the distance is also increasing. So there is what we call as constant speed there. So there is constant speed. This is moving, this is increasing, and that is also increasing. There is speed there. So when we reach from A to B, since we are dealing with the distance, you see that distance is no longer moving, going up. Distance is no longer, here speed is increasing, constant, at a constant rate, it's increasing. Okay, there is acceleration here. So acceleration is when speed is increasing consistently, it's just increasing, it's not constant. So like when you are, maybe you have just started the car and you press the pedal, so the car will be accelerating, it will be moving, it will be increasing the speed gradually, it will keep on increasing the speed. Okay, so now we are saying since here there is acceleration from A to B, you see acceleration has to do with time and velocity. So if we say there is no, if the distance is not moving here, yet time is moving, in this case it means that object or the vehicle, whatever it is, it has stopped moving, because it's only time that is moving. You can imagine you start off from home, you go, there's no time here, there's zero time and there's zero distance, so you're at home. So you move for x time in you move for h distance in x time. Let's say maybe this is 5 kilometers. You move the 5 kilometers in 1 hour. So you have reached the market. Then at the market here you stop. You stop moving. Time will be moving. Time will not stop because you have stopped your journey. Okay? The time will be moving from x to eventually go to y. So from there now, you start going back home. This is what the whole graph is talking about. So when you're dealing with this distance time graph, this tells you that there's no distance being covered, because distance has to go up for distance to be covered. So this tells us that here there's no distance covered. So the object is at standstill. Whether it's a car or whatever it is, it has stopped. Now, when we talk of velocity time graph, when we talk of velocity time graph, when we talk of velocity time graph, what we have is we have time in seconds, we have meters per second velocity there. So with velocity, what it means here is when you are here, if it's a car, it is parked here. So the moment you press on it, it starts accelerating. The speed is increasing as time is increasing. As time is moving, the speed is also moving, and it's moving gradually. Okay, so this is the part here. So here you are accelerating. The moment you reach A, and then the graph becomes like this. Imagine if this was 10 meters per second, if this was let's say 20 meters per second, it means this is the current speed that the vehicle has. So it will continue moving with this speed. Okay, it will continue moving at this speed from A to B. The speed is constant. This is what it means. It's different from distance time graph, because distance time graph, it means you are not moving. Only time is moving, distance is not moving. But here, when you are moving, you start from zero, you accelerate, you reach 20 meters per second, then you move constant. You have not stopped, you are moving at a constant speed. You only stop when you go back to this line here, because you would have reached the zero velocity. So when velocity is zero, it means you are not moving. That's what that means. So acceleration, so I'm saying acceleration can be calculated as final, let me say, I didn't want to just talk about acceleration before explaining what it is. So I'm saying acceleration is equal to final velocity minus initial velocity divided by the time taken. Okay, so that is what we have there. So final velocity minus initial velocity divided by the time taken. So there are initials that we use. So you can simply say A is equal to, for final velocity we use V, for initial velocity we use U, and then for time we use T. So this is the formula we can use to solve for acceleration. Okay, so now that's what we needed to know there. Now let's try to combine them with force, because that question we have, it has got this part we have talked about is there, and also force is also there. So let's briefly talk about force and then combine the two to work out the certain problems that we have. So let's talk about force. Okay, so what is force? Mommy. Wow. Okay. Sorry for that. So we are saying force. When you want to define force, is simply a push or a pull. So force is a push or pull. Okay. So when you push something, you are applying force. When you pull something, you are applying force. When you enter those big doors at in these most of these shops, say that they write pull or push, or even in the banks. So the doors that are there is either it's written outside, it may be written pull or push, or inside it can be written pull or push. So you're applying force there when you pull it or when you push it. So force is simply a push or a pull. So Also, we need to know that force is actually a vector quantity, because when you are pushing in a certain direction. You are not just pushing anyhow. So force is a vector quantity. So I'm saying this is a vector quantity because it has got both magnitude and direction. How much force are you putting? That's magnitude. Which direction are you pushing it in? That's the direction. So vector quantities have got both magnitude and direction. And then the SI unit for force, the SI unit is simply newtons. Okay, newtons. We use the capital letter N for newtons. Okay, why is it called Newton? Because it's named after the discoverer, who is Sir Isaac Newton. So that's why it's called the newtons. Okay, so now what else can we talk about force? Let's talk about effects of force. Okay, let's talk about effects of force. So force can change motion. Okay, so force can change motion. Okay, so force can change motion. It can either start an object that is at standstill, like this object here, it's at standstill. So when I apply force, it will move. So this is what force can do. When you apply force to this, it moves. Okay, you apply force to it, it moves. So force can change motion. Or maybe if it was moving and then you apply force, then it can stop. That's what force can do. Or when if it was moving, it was moving slowly, then you apply force, it can move faster. So that's what force can do. Or it was moving faster, you apply certain force from depending on the direction you're applying it from, it can either reduce instead of increasing. So all those are effects of force. We are saying it can change the motion. Okay, so it can also change the shape. It can also change the shape of an object. Okay, so you and I agree very well, so much that force indeed can change the shape. So if I was to ask you anything that can change shape after you apply force, who can quickly tell us anything that you feel can change after the shape can change if you apply certain force? Quickly, any example? Okay, seems to be quiet. Let's talk of an egg. If you press an egg with certain force, it will break, the shape will change. If you pull a string, what's this, a rubber band, okay, if you have a rubber band like this, then you pull it from here, you hook it here and pull it towards that direction, you realize that it will become something like this. Okay, when it was just straight, when you pull it down, it will become something like this. Okay, so it can change the shape. So shape can change. You press an egg, it will break. So, and so many other things that we can think of that can change when force is applied to them. Okay, so the other thing also we need to know is that it can also cause rotation. So it can also cause rotation. Okay, so the moment you apply force, it can cause rotation. Like even on a bike, if you have seen a bike before and those that ride it, so when you press force, on the pedal, you press the force on the pedal here, it turns. Okay, so the force causes the turning or the rotation. Okay, so this is also what we have to say about force. So let's talk about something else also, because we have said it can change the motion. let's talk about the unbalanced force. Okay, let's talk about the unbalanced force. Okay, so if we have two forces that are acting on a body, then we are going to have what we call as the resultant force. For example, what I'm talking about is, for example, if we have this body here that is lying on the floor, and then we have two forces acting on it. We have maybe, let's say, 5 newtons, and the other one we have 4 newtons, and then here we have 7 newtons. So we have this body here, and we have those forces that are acting on it. Now you see that this side there's 7 newtons that is pulling it this side, and the other side there's 5 plus 4, which is 9 newtons. So you see that this part has got 2 newtons extra, because you're going to say, okay, 5 plus 4, 5 newtons plus 4 newtons minus 7 newtons. So this is going to be 9 newtons minus 7 newtons, which is 2 newtons. So the 2 newtons is what we are referring to as the unbalanced force, or the resultant force. Okay, so the unbalanced force, or what we are calling as the resultant force. And now, in which direction? Since the right part has got more, okay, so meaning it will move to the right, okay, to move to the right direction. So this body will move towards the right direction, because the right direction has got the bigger forces compared to the left direction. So this is how we find the unbalanced force, or the resultant force. So you simply check which one has got more. If there are 3, you add all of them and subtract the smaller from the bigger, depending on the two sides. Or if you have one force here, one force, you subtract them, find the difference. If the two forces are going to be the same, let's say if we have the two forces, if we're going to have something like this, we have something like this. We have 3 newtons pulling that side and 3 newtons pulling this side. Do you think this object is going to move, in your own opinion? This object A, do you think it's going to move? Okay, so when I ask questions, I actually mean that you should respond. I don't know why you are not responding. Anyway, so since there's 3 newtons pulling this side and there's 3 newtons pulling this side, so these forces are equal. So this object is not going to move anywhere, because the two forces that are pulling each other, we can say 3 newtons minus 3 newtons, then we have 0. So we have 0 resultant force. There's nowhere that object is going to go. It will just remain static there. It will not move to any direction, because the forces that are pulling on both sides are actually balanced. So there's no force that is overcoming the other. If you remember the tug of war, where you put a rope and then others are pulling this side and others are pulling the other side, then there's a finishing line here. So there's this rope and there's a line down there. So here you have people pulling, and the other side you have people pulling. So as you are pulling, we see whoever, if this group is going to be pulled until they cross the line, then they have lost. So this is what happens here also. So when you look at this force is pulling, and here 5 is pulling, and then the 4 also pulls. You realize that this side they are going to win, because resulting this, when you add them, you get 9 newtons. So this object is going to be moved towards that direction. So that's what we have there. Okay, so let's talk about, since we have talked about newtons as the originator, or the man behind the SI unit newtons. So let's talk about Newton's laws of motion. Since we're talking about motion here, and the question when you look at it, it's all about motion. So we have Newton's laws of motion. Okay, so there are basically three laws of motion that Newton came about. Okay, so the first one is that a body, okay, so the first one says a body continues in motion. Okay, so a body continues. I'm just paraphrasing though. So a body continues in motion, continues in a constant motion. Okay, so a body continues in uniform or constant motion. Okay, on a straight line. On a straight line. Okay, it moves in a it continues in the uniform motion on a straight line. Okay, or when it's resting, or when it's at rest, it continues also resting. Okay, on a straight line, or when at rest, continues in uniform motion on a straight line, or when at rest. What I'm trying to say here, even when it is at rest, it continues in the same state of resting, not until, or we can say unless an outward, okay, unless an outward force, or we can simply use external, unless an external, meaning a force from outside, an external force is applied to it. Okay, so if an object is moving at a uniform speed or uniform motion, it will continue moving on a straight line, not until some external force comes to disturb it. Okay, like we said, force can either increase the motion or reduce the motion, or can stop the motion, or can actually start the motion. So this is Newton's first law of motion. Then the second one says unbalanced force, an unbalanced force acting on a body, so an unbalanced force acting on a body produces an acceleration, produces an acceleration in the direction of the force. In the direction of the force. Okay, so the example I gave of an object that is, so we are saying an unbalanced force. Of course, we discovered what unbalanced force is. If we have, this is our object here. For instance, the previous example we had, so we have this our object here, which is the duster. So we had 9 newtons here, and we had 7 newtons there. Okay, so now we see to it that 7 is less by 2 newtons on the other side. This is left, this is right side. So the unbalanced force is these 2 newtons, which is the difference. When you say 9 minus 7, you get 2. So the 2 newtons, which is the difference between these two forces, that's what we are calling as the unbalanced force. So we are saying the second law of motion says An unbalanced force, which is these 2 newtons, acting on a body, acting on this one, produces an acceleration. So meaning this will start moving in the direction of the force. So since the unbalanced force is this side, the extra 2 is this side. So this thing will start moving towards this side. Following, because this is where the resultant force is. So it moves from here, it starts moving towards the right. Okay, because that's where the resultant force is. So that's what this second law of motion is actually talking about. So let's go to the third law of motion. Third law of motion. And also the one thing I forgot there is that on the second law of motion, so the force that is applied here, the same unbalanced force, so the same unbalanced force F is directly proportional to the acceleration, mass times acceleration. So force is direct proportional to acceleration there and mass. So hence giving us the formula for finding the force that has acted on the object to be mass times the acceleration. So the mass of the object times the acceleration that has been caused by the force, then we get the force. Also the weight, if we have the weight, so I'm also saying weight is equal to mass times gravity. Okay, so that is direct proportional as well. So it comes from the second law of motion, Newton's second law of motion. So the third Newton's law of motion simply is the simplest of all, and it's the most practical. So the third one says, so to every action or force, there is an equal and opposite reaction. There is an equal and opposite reaction. Okay, so to every force that can be applied on anything, there is usually an equal and opposite reaction. So what Newton was trying to say here is, when you sit on a chair, okay, you sit on a chair, okay, you sit on the chair like that. So when you sit on that chair, the force that you are putting on the chair here, it means the chair is also putting the same force. It's reacting with exactly the same force that you are putting on it. What this simply means is that should you apply more force than what this chair can put, it means the chair is going to break. Okay, so when you sit on the chair, always remember that the chair is also putting back the same force as what you have put there. Okay, such that when you put more than what it can push up there, what it can react to your force, then the chair is going to break and it's damaged. So to every force there is an equal and opposite reaction, and this is what perhaps brings about friction. So this is what brings about friction. So when you talk of friction, you see this board here. When I'm trying to push it this side, it's stuck to the board there. This duster, when I'm pushing it, is stuck to the board. So I need to put more force, because there's a force down there which is holding it, and that is what we are calling as the friction force. And usually friction force acts in an opposite direction. So when I'm pushing like this, the force is acting this way. so that it's trying to avoid this object from move. So the friction force says, no, 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 you're not going to move this object. It's holding it until you apply more force than what is saying don't move it. So until the force I apply here becomes more, then this thing is going to what? Move like that. So that's what we are trying to say. So to every force there is equal, there is same, equal and the opposite force that is actually exerted or given. So let's look at some few examples. One or two. Yeah, let's look at one or two examples. Then we see what follows. Okay, so example number one, we are saying a sledge of mass 25 kg is pulled across level ground, okay, with a horizontal force of 60 newtons. So there is this sledge that is being pulled across the level ground with a horizontal force of 60 newtons. So we are saying the constant force of friction, the constant force of friction is 20 newtons. What is the acceleration of the sledge? Okay, so the sledge we are talking about, if you have been to if you grew up from a farm or a village, you realize that there was this thing that we cut from a tree. You cut it from a tree, and then it's the one that we use to put things when you're going to the fields. So it's something like this, and then you hook it with a chain, and then here you have your animals. Okay, you have your animals. Okay, okay, so you have your animals, they are pulling this thing here. So that's what we are calling as, that's an example that I can give of a sled. But when you go to our friends who are living in the snow, they have those things that they put. It's a very nice thing that is made, that has to be put along the ice there, and it's moving. Okay, so now this is the thing that we are talking about here. Let's use what we understand in Africa. So I'm saying this sledge of mass 25, so this has mass 25 kgs. So it has mass 25 kgs. Okay, and then this mass 25 kg is we are saying is pulled across the level ground. So it's being pulled across the level ground with a force, a horizontal force of 60 newtons. So the force that is pulling here is 60 newtons. So we have that force of 60 newtons pulling that sled there. The constant force of friction, so the force that is refusing to say no, don't move, which is pulling towards the other direction, okay, is 20 newtons. 20 newtons is the friction force. So now we are being asked, what is the acceleration? What is the acceleration? Okay, so what is the acceleration of this sled? So from the second law, Newton's second law of motion, we have that force is equal to mass times acceleration. Okay, F is equal to m times a. So this is what we get from this Newton's second law of motion. So now from this we find that we have the force we have, the mass we have, then we want to find the acceleration. So let's try to make acceleration the subject of the formula here. We divide through by m. So acceleration will be, acceleration is equal to force over mass. That is what we have. Now remember that for this thing to move, we are talking about the resultant force. That is what is making this to move. Okay, so how do we find the resultant force? We have the 60 pulling this side, we have the 20 pulling the other side. So the resultant force which is making it move, for it to have the acceleration we are talking about. Okay, so we're going to say 60 newtons minus 20 newtons, then we get 40 newtons. So this 40 newtons is the force that is making it move. Okay, because there is this 20 which is refusing. So when, if here it was 20, this would not move. So now when it becomes, when you from to the 20, which is exactly the same as what is pulling this side, and also if we put a 20 at first, then we say, okay, let's add 40 more. So we add 40 more newtons the other side does in terms of force. Then we see this starts moving. And as it is moving, we are saying it's moving towards this direction because the resultant force is towards the right, and the resultant force is 40. So you don't just go ahead and pick the 60, put there, get the mass, put there. No, that will not be correct. So you need to use the resultant force there. Since the 20 is going, oh, besides, which one are you going to use? There's 20 which is pulling this side, and there's 60 which is pulling the other side. How do you just decide to say, okay, let me use this one? So the idea is, since this one is pulling this side, for this thing to move, this 20 has to be overcome by the other force. So the other, for it to move, you have to overcome the 20. So meaning from this 60 subtract the 20, the 20 will go to balance up, they will be balanced, and then the moment it exceeds 20 this side, then this thing will start moving. So that's why we are subtracting a 20 from the 60 to get that 40. Okay, so meaning what we have now here is acceleration is equal to 40 over 25, which gives us acceleration is equal to, when you divide 25 into 40, you get something like 1.6 meters per second squared. Kindly check this answer at your own free time and let me know whether that answer is correct. So that's what you get there. Okay, let's do the another example. Let's do another example. Example 2. Let's do example 2. I was impressed with how you solved the question for biology. I was very much impressed because we ran out of time and we are not able to solve the question from the past paper, but I used the same question in the past paper as an exercise, and you did it very well, excellently, such that I even thought maybe you were copying from somewhere. So let's look at the second example. We're saying a small submarine of mass 1000 kg sinks, I hope this is not the Titanic, sinks in water with a uniform speed of 2 meters per second. So we have this submarine Okay, so we have our our submarine, a mini or a small submarine. So now there's a question here, which is this one now. There's a question which says, what is the resultant? What is the resultant force exerted on the submarine as it sinks? As it sinks. Okay. Now, here we need to be very careful. As we are told that a small submarine of mass 100 kg sinks in water with a uniform speed of 2 meters per second. Then what is the resultant force exerted on the submarine? Now remember, when I did the speed time graph, I gave you something like this. Okay, if this was A and this was B, let's use this one. So we are saying from 0 here, then here we have 2 meters per second. So this thing has moved, and then there's time here, whatever time t. So this submarine has moved from start there as it starts sinking. So now we are not told how the acceleration. We're not told the acceleration, but all what we are told is this is like it started sinking at point A. So it started sinking here, going down. So we're told that it is sinking in water with a uniform speed. This is the key word here. Uniform speed. So this is only part where we have the uniform speed, which is 2 meters per second. So throughout this line, we have 2 meters per second. So this is the uniform speed it is sinking at. Now here, there's no acceleration here from A to B. Here, there's no acceleration. Okay, acceleration is only here where we see time, distance moving at the same time. Time increases speed, not distance, sorry. So time is increasing, the speed is increasing. As it is increasing like that, that's when we have acceleration. When it's only when speed has stopped increasing, it's constant, and then it's only time that is moving. There's no acceleration there. So we needed to be very careful on that one. So this ship, this submarine, as it is sinking, it was not accelerating at all. So now when we come to our formula for the second law of motion, Newton's second law of motion, we're going to say force is equal to mass times acceleration. So the moment acceleration is equal to 0, then we have 0 times whatever mass that we have. Then meaning the resultant force is going to be 0 newtons, because there's no acceleration, because 0 times the 1000 mass, perhaps let's just do it so that we don't mess up. So it will be F is equal to mass is 1000 kgs, so 1000 kgs times 0 meters per second squared. So because 0 times 1000 you get 0, so you're going to have 0 newtons. So that is the resultant force which